a SpaceX rocket secretly intercepted an object from another star. This was the incredible story that recently went viral, painting a picture of a clandestine mission to a 7-billion-year-old comet. But is there any truth to it? The real story is a deep dive into physics, astronomy, and the immense challenges of space exploration. It reveals not a conspiracy, but a profound question about our readiness to meet the universe head-on. Let's break down the science and explore the why. What makes 3I Atlas special? First, why does an object like this even matter? Imagine holding a rock that formed billions of years before our own planet. That's the level of importance we're discussing. While the name 3I Atlas is fictional, it's a clear stand-in for real visitors like Comet C 2023, A3 Tsuchinshan Atlas. That specific comet hails from our own solar system's Oort cloud, a massive theoretical sphere of trillions of frozen objects orbiting our sun up to a light-year away. But true interstellar objects like 1I Oumuamua and 2I Borisov are far more exotic. Oumuamua, discovered by astronomer Robert Warwick in 2017, was a 400-meter-long enigma traveling at a blistering 87.3 kilometers per second relative to the Sun. 2I Borisov, spotted by Gennady Borisov in 2019, was moving at an equally impressive 32 kilometers per second. Their velocities are so high they can only be achieved by objects falling into our solar system from the vastness of interstellar space. They are in essence geological samples from other solar systems, offering us a direct look at the chemistry that forms planets around other stars. Analyzing just a few grams of this material could reveal a chemical fingerprint, a set of isotopic ratios, completely alien to our own cosmic neighborhood. The Falcon 9 connection debunked. So what about this sensational claim that a Falcon 9 chased one down? Let's look at the science and why that's physically impossible. A SpaceX Falcon 9 is an incredible machine, a workhorse that has launched over 100 times in a single year, making space access routine. But its entire design is optimized for one primary task, delivering payloads to Earth orbit. It's built to produce a massive burst of thrust from its 9 Merlin engines to overcome Earth's gravity and place a satellite like one of the 23-ton Starlink batches into a precise orbit roughly 550 kilometers up. It is fundamentally a launch vehicle, a brilliant first stage, not a deep space cruiser. The idea that it could turn on a dime and chase an object millions of kilometers away, moving at over 100,000 kilometers per hour, is a fundamental misunderstanding of its purpose. It simply does not carry the propellant, nor does it have the high-efficiency engine systems like ion drives that are designed for sustained, multi-year travel and maneuvering in deep space. It's like using a world-class sprinter to try and win the Tour de France. Both are elite athletes, but they are built for entirely different arenas. The physics of interception. To understand why interception is so hard, we need to talk about delta V. In rocketry, delta V is the ultimate currency. It measures a spacecraft's ability to change its velocity. Every maneuver costs delta V, and you only have what your fuel tank allows. Getting a satellite to low Earth orbit requires a delta V of about 9.4 kilometers per second. But to chase down an interstellar object? A detailed study for Project Lyra by the Initiative for Interstellar Studies calculated that intercepting Oumuamua would have required a delta V of more than 30 kilometers per second, and possibly as high as 70 kilometers per second, depending on the timing. That is an enormous energy gap. For comparison, our fastest spacecraft, the Parker Solar Probe, will reach 192 kilometers per second, but it will take 7 years and 7 gravity assists from Venus to do so, using the Sun as a giant gravitational slingshot. It also required a Delta IV Heavy rocket, far more powerful than a standard Falcon 9, just for the initial launch. The bottom line is that catching these objects isn't just a matter of pointing and shooting. It requires an almost unimaginable amount of energy planned years in advance. Alien chemistry possibilities. This is where the science gets truly exciting. What if these interstellar visitors contain a chemistry alien to our own? Any object that formed around another star would have been built from a unique nebula with a different chemical makeup. Observations of 2I Borisov, led by scientists such as Denis Bodowitz, showed it contained up to 26 times more carbon monoxide than a typical solar system comet. This points to it forming in an extremely cold carbon-rich environment very different from our own. This leads to the ultimate question, one often raised by Harvard astronomer Avi Loeb: could these objects carry the building blocks of life but with a different twist? Life on Earth is based on left-handed amino acids, a specific molecular orientation known as chirality. What if we found right-handed versions or entirely new types of amino acids not found in the Murchison meteorite or other local samples? This discovery would provide powerful evidence for panspermia, the theory that life's ingredients are transported between star systems. It would mean the recipe for life is common in the galaxy, but that it might have different regional dialects. It would be the first concrete evidence of an alien biochemistry. 3 missed opportunities. The story of interstellar visitors so far is a story of missed chances. We've had 3 clear opportunities and we've watched each one fly by. The first was one Oumuamua, spotted on October 19, 2017. The astronomical community was in shock. Nothing like it had ever been seen. But by the time Robert Warwick and his team understood its significance, it was already hurtling out of our solar system, too far and too fast to catch. Its strange shape and behavior remain a scientific puzzle. Then, on August 30, 2019, Gennady Borisov found 2 I Borisov. This one was a gift because it was more comet-like, with a visible coma of gas and dust stretching nearly 160,000 kilometers wide. This allowed for spectroscopic analysis from Earth, giving us that tantalizing data about its carbon monoxide content. But again, the launch window was impossibly short. There was no spacecraft ready to go. The reality is that building, testing, and launching a deep space mission takes years, and these objects give us only a few months of warning. Each of these flybys was like an unopened letter from another star system that we could read the address on, but couldn't actually open. Future intercept technology. So, are we destined to keep missing these opportunities? The European Space Agency says no. Their solution is the Comet Interceptor mission, slated for a 2029 launch on an Ariane 6 rocket. This is a brilliant piece of long-term planning. The spacecraft will not have a pre-selected target. Instead, it will fly to the Sun-Earth Lagrange Point 2, a gravitationally stable location 1.5 million kilometers from Earth, and it will simply wait. This parking spot allows it to loiter for up to 3 years, acting as a cosmic sentry. When a suitable target is found, likely by the upcoming Vera C. Rubin Observatory in Chile, the mission will begin. That observatory, with its 8.4-meter mirror and 3.2 gigapixel camera, will scan the entire sky every few nights, making it the perfect tool for finding these fleeting visitors. Once Comet Interceptor gets its target, the main craft will deploy 2 smaller probes. Together, the 3 will fly through the comet's coma in formation, creating a 3-dimensional snapshot of its nucleus, gas, and dust with instruments like mass spectrometers and plasma imagers. This is our first real practical plan to get up close and personal. Scientific implications. So let's focus on the scientific payoff here because honestly it would be enormous. Intercepting one of these objects would move us from theory to fact on some of humanity's biggest questions. First, by analyzing its composition and isotopic ratios, the unique signature of neutrons in its atoms, we could get a definitive fingerprint of another solar system's planetary nursery. Different stars forge elements in slightly different ways, so this would be like a birth certificate for the object's parent star. Second, as scientists like Avi Loeb have pointed out, we should be prepared for the unexpected. A detailed chemical analysis could reveal biosignatures or even technosignatures that are completely unanticipated. Most profoundly, finding unique organic compounds or amino acids would provide the first direct evidence for panspermia, the idea that the ingredients for life are common throughout the cosmos. This isn't just about rocks and ice, it's about understanding our own origins, the potential for life elsewhere, and our ultimate place in the universe. Trajectory analysis and mysteries. So how do we know for certain they are from interstellar space? The answer is in the geometry of their orbits. Everything in our solar system follows a closed elliptical path. These visitors, however, are on a hyperbolic path. It's a one-way ticket. They fly in, loop around the sun, and fly back out, never to return. Their extreme speed prevents the sun's gravity from capturing them. But the trajectory of Oumuamua held a deeper mystery. A team led by Marco Micheli of the ESA confirmed it had a slight non-gravitational acceleration. It was being pushed by something other than gravity, at about 1.5 millimeters per second squared. The leading scientific hypothesis, championed by astronomers like Jennifer Bergner, is that this was caused by the outgassing of trapped hydrogen ice as it was warmed by the sun, creating an invisible, rocket-like effect. But because this couldn't be visually confirmed, the puzzle remains, fueling all sorts of speculation. This single data point shows how little we know and why getting close-up data is so critical. The official facts. To ground this discussion in reality, let's review the verified data for Comet C 2023 A3 Tsuchinshan Atlas. It was first imaged on January 9, 2023, and officially confirmed on February 22, 2023. The Atlas survey that helped find it is a network of telescopes designed specifically to find near-Earth objects. This comet is from our Oort cloud, not another star, with an orbital inclination of 139 degrees. Its perihelion, or closest approach to the Sun, was on September 27, 2024, at a distance of about 58 million kilometers. It passed closest to Earth on October 12, 2024, at a safe distance of 71 million kilometers, reaching a peak brightness that made it visible with binoculars. Its nucleus is estimated to be several kilometers in diameter, and to be absolutely clear, no spacecraft, Falcon 9 or otherwise, has intercepted it. The viral story was an exciting piece of fiction, but the real comet and the real science are arguably even more compelling. The bigger picture. The false Falcon 9 story, while incorrect, forces us to look at a larger truth. We are at a turning point in human history. For the first time, we possess the technology to not only see these interstellar messengers, but to actively chase them. With new telescopes like the Vera C. Rubin Observatory coming online, its director, Zeljko Ivazic, has predicted we may soon spot dozens of these objects every year. The question is no longer one of capability, but of will and preparation. Do we invest in a permanent rapid response intercept program? Missions like Comet Interceptor are the first step, but a dedicated program would ensure we never miss another opportunity. This is a strategic decision about our future as a spacefaring civilization, akin to the commitment made during the Apollo era. The choices we make in the next decade will determine whether we become active explorers of the galaxy or remain passive observers, watching the biggest discoveries fly right by us. So, while a Falcon 9 didn't actually intercept an alien comet, the underlying science is what truly matters. We now know our solar system is visited by objects from other stars, carrying clues to some of the universe's biggest mysteries. The next one is already on its way. What do you think humanity should do to be ready for it? Let us know your thoughts in the comments. Don't forget to like, subscribe, and hit the bell icon to join us as we continue to explore the Psi and Why. Thanks for watching. NASA's James Webb Space Telescope has achieved a groundbreaking feat by capturing the first real image of the enigmatic interstellar object 3Y Atlas. This remarkable milestone opens a new chapter in our understanding of cosmic wanderers and the mysteries they hold. The data reveals unprecedented details that challenge previous notions about interstellar visitors. Join us as we unravel the story behind the flicker in the telescope's data leading to this profound discovery, the object's incredible speed from the void, and the secrets it may unlock about our universe. The flicker in the data. In late 2025, astronomers noticed a faint flicker within vast datasets collected by advanced telescopes across multiple observatories worldwide. Initially dismissed as background noise or instrumental error, this subtle signal sparked curiosity among researchers at NASA when artificial intelligence algorithms began flagging anomalous patterns. Analysts utilized cutting-edge machine learning algorithms to isolate these anomalous data points corresponding to an object moving at extraordinary speed through our galaxy. Subsequent observations confirmed the flicker as 3Y Atlas, a massive interstellar visitor entering our solar system from the depths of space. This serendipitous detection was a testament to the increasingly sophisticated analytical methods enabling the discovery of elusive cosmic travelers from the vast interstellar void. The discovery process highlighted how modern astronomy relies on both advanced technology and human intuition to identify phenomena that would have been completely invisible to previous generations of scientists. The flicker represented humanity's first glimpse of what would become the most significant interstellar discovery since Oumuamua, offering unprecedented insights into phenomena previously beyond our reach and understanding. 152,000 miles per hour from the void. 3I Atlas barrels through space at a staggering velocity of approximately 152,000 miles per hour, or about 68 kilometers per second, defying all known celestial norms and expectations for objects in our cosmic neighborhood. This extraordinary speed has been confirmed through precise orbital tracking conducted by teams at NASA's Jet Propulsion Laboratory, utilizing multiple ground-based and space-based observation platforms. The velocity calculations show this speed dwarfs any traditional simulation of interstellar objects passing through our solar system, suggesting origins from an incredibly distant star system. Such immense velocity indicates the object has traversed the vast interstellar void for potentially millions of years, subjected to cosmic radiation bombardment and gravitational perturbations from countless stellar encounters. Its trajectory through the ecliptic plane positions it for brief but critical visibility windows, prompting astronomers worldwide to mobilize for intensive observation campaigns using every available telescope and sensor array. Understanding this rapid journey through space enhances our fundamental grasp of galactic dynamics and the frequency of alien visitors crossing our cosmic neighborhood, while raising profound questions about the forces that could accelerate such massive objects to these incredible speeds. 3 visitors, 7 years. Since the epical discovery of Oumuamua in 2017, followed by the comet-like 2I Borisov in 2019, humanity has witnessed 3 confirmed interstellar intruders within a span of just 8 years. This unprecedented sequence has fundamentally transformed our perception of the solar system's place within the broader galactic environment and the frequency of cosmic visitors. Each visitor displays unique physical and dynamic attributes, painting an increasingly complex picture of materials ejected from diverse planetary systems across the galaxy. The arrival of 3I Atlas, significantly larger and faster than its predecessors, magnifies the urgency in understanding the true diversity and origin of such objects in our cosmic neighborhood. As observational technology advances and detection methods become more sophisticated, the frequency of such encounters may reveal long-hidden cosmic realities about interstellar traffic patterns. The pattern suggests that interstellar visitors may be far more common than previously imagined, fundamentally challenging our understanding of solar system dynamics and the movement of matter between star systems. These discoveries collectively indicate that our solar system exists within a much more active and dynamic galactic environment than scientists previously recognized, with implications for planetary formation, asteroid populations, and the potential for life-bearing materials to travel between worlds. James Webb's metallic discovery. So James Webb's metallic discovery, well, the James Webb Space Telescope's recent high-resolution imaging of 3I/Atlas, has delivered completely unexpected revelations about its surface properties and composition, and honestly, these findings have just stunned the scientific community. Comprehensive spectral analysis, which was conducted by Dr. Liam Cheng and his international research team, detected a predominantly metallic composition. This fundamentally challenges those long-held assumptions that interstellar objects are mostly icy or rocky bodies. Now, this distinctive metallic signature, it suggests either advanced natural processing through some truly extreme cosmic conditions, or, potentially, artificial construction by unknown technological means. Reflected light patterns captured by Webb's advanced infrared instruments indicate an unusually smooth, potentially engineered surface, instead of the rough, pitted texture that's typical of natural asteroids or comets. The metallic composition even appears to include elements not commonly found in typical solar system objects, like rare earth metals and isotopes that suggest formation under, well, exotic stellar conditions. These groundbreaking findings open the door to revolutionary hypotheses regarding non-natural origins, and they're really compelling scientists worldwide to expand their investigative methodologies and fundamentally reconsider their definitions of cosmic phenomena. The discovery has prompted emergency funding for additional observation time, and it's sparked some intense international collaboration to analyze every detail of this unprecedented visitor before it disappears forever into the depths of space. The machine that steers itself. This is honestly one of the most astonishing and scientifically challenging aspects of 3I/Atlas. It's the object's apparent ability to modify its trajectory mid-course, which strongly implies the presence of an intrinsic navigation or guidance system. Groundbreaking research led by aerospace engineer Dr. Sofia Martinez has documented subtle but measurable variations in velocity and orientation that just remain completely inconsistent with gravitational influences alone. These adaptive steering capabilities suggest highly sophisticated onboard systems, either responding intelligently to external stimuli or fulfilling some form of pre-programmed interstellar mission. This phenomenon, well, it raises some profound and honestly unsettling questions about whether such objects represent autonomous probes, rather than just mere geological debris drifting through space. The trajectory adjustments seem to occur at specific intervals and follow patterns that suggest deliberate course corrections, probably designed to optimize the object's path through our solar system. Such capabilities would require technology far beyond anything currently possessed by human civilization, involving either advanced artificial intelligence or direct control by some form of intelligence. The implications here challenge existing space exploration frameworks, and they invite some pretty serious speculation about extraterrestrial engineering and the possibility that 3I/Atlas represents humanity's first encounter with genuine alien technology actively operating within our solar system. Information blackout. Despite intense scientific scrutiny from observatories worldwide, much crucial information about 3I/Atlas still remains, well, mysteriously enigmatic due to unprecedented government-imposed data restrictions and communication blackouts. Classified satellite data and systematic communications jamming really hint at a broader, coordinated information suppression campaign designed to deliberately suppress sensitive knowledge regarding the object's true nature and potential origins. Whistleblowers, including former intelligence officer Dr. Eleanor Hayes, suggest that agencies across multiple governments participate in coordinated secrecy operations that span international boundaries. This systematic information blackout has fueled widespread conspiracy theories and public frustration, while at the same time underscoring the immense challenges legitimate scientists face in accessing comprehensive datasets needed for proper analysis. The restrictions appear to target specific wavelengths of electromagnetic observation and particular types of gravitational measurements, which suggests authorities know exactly what they want to conceal from public knowledge. Transparency advocates and scientific organizations worldwide argue vigorously for immediate declassification to advance scientific understanding and, properly prepare humanity for potential first contact scenarios. The secrecy has created an unprecedented divide between official government statements and the growing body of leaked evidence, suggesting 3I/Atlas represents something far more significant than a simple interstellar asteroid. Adaptive shielding technology. So, recent theoretical models developed by leading physicists propose that 3I/Atlas employs this, highly advanced adaptive shielding technology. It's apparently capable of rendering it nearly invisible to conventional detection methods, and that's across multiple electromagnetic spectra. The Max Planck Institute, they've elaborated on these sophisticated hypotheses involving electromagnetic cloaking fields and dynamic surface morphing, which could help explain the object's, mysteriously elusive signatures. Such revolutionary shielding technology would, at least in theory, allow the object to systematically evade host planetary defense systems and observational arrays, basically making completely discrete movement through solar systems possible. The proposed technology involves real-time manipulation of electromagnetic properties, possibly through programmable metamaterials that can alter their reflective and absorptive characteristics instantaneously. Investigations into these extraordinary properties may, honestly, revolutionize human understanding of stealth technology, with some pretty profound implications for both planetary defense systems and future space exploration capabilities. The adaptive shielding seems to actually respond to different types of observation attempts, becoming more transparent to certain wavelengths while staying opaque to others, in patterns that, suggest intelligent control. If confirmed, this technology would represent a quantum leap in material science and electromagnetic manipulation, far beyond anything achievable with current human knowledge, and could potentially provide blueprints for revolutionary advances in spacecraft design and planetary protection systems. The Ancient Probe Network. So, emerging evidence increasingly suggests that 3I/Atlas might represent a crucial component of a vast ancient probe network, potentially constituting a galactic surveillance system initiated by an advanced civilization that predates human existence by millions of years. Leading astrobiologist Dr. Maya Singh describes how such interconnected probes could, in theory, monitor planetary systems across thousands of light-years, relaying comprehensive information through quantum entanglement communication systems or, even faster-than-light transmission methods. These sophisticated networks might encode prime number sequences within their thermal signatures, functioning as distinguishing identification markers or complex mathematical messages designed for detection by emerging technological civilizations. The probe network theory, honestly, suggests a level of galactic organization and long-term planning that completely transcends human technological capabilities and temporal perspectives. Each probe would operate semi-autonomously while maintaining connection to a larger intelligence network, gathering data on planetary development, biological evolution, and technological advancement across, countless worlds. Such a discovery would fundamentally redefine humanity's place in the cosmos, indicating we exist within a much larger, interconnected interstellar intelligence system that has been operating for eons. The implications extend really beyond mere scientific curiosity, suggesting that human development may have been observed and possibly influenced by these ancient sentinels, heralding a new era in astronomical, philosophical, and existential understanding of our role in the universe. Prime numbers in heat signatures. Scientists analyzing the thermal emissions from 3I/Atlas have detected increasingly intriguing patterns featuring prime number sequences, which, many researchers interpret as deliberate mathematical signals rather than just random electromagnetic noise. A renowned mathematician emphasizes that these precise numerological features could represent a sophisticated, intelligent encoding method, strongly indicating deliberate communicative intent from the object. These remarkable findings add substantial credence to the hypothesis that 3I/Atlas represents an artificial probe, and they've sparked unprecedented new interdisciplinary studies combining advanced astrophysics with information theory and cryptographic analysis. The presence of prime number sequences in electromagnetic emissions is widely considered among scientists as, honestly, potentially universal evidence of technological civilization, effectively bridging the gap between purely cosmic phenomena and potential extraterrestrial intelligence communications. The patterns appear in multiple frequency ranges and follow mathematical progressions that would be, virtually impossible to produce through natural processes alone. The sequences begin with simple primes like 2, 3, 5, and 7, then progress to increasingly complex mathematical relationships that suggest a deliberately constructed communication protocol. International teams of mathematicians and physicists are working around the clock to decode additional layers of meaning embedded within these thermal signatures, while astronomers continue monitoring for any changes in the transmission patterns that might indicate active communication attempts or responses to human observation efforts. We were never the observers. The revolutionary notion that humanity has never been the sole observers of the cosmos is, honestly, gaining unprecedented traction through intensive study of 3I/Atlas and its profound implications for our understanding of galactic civilization. Ongoing research strongly suggests that Earth has been an integral part of a carefully monitored network within a complex universe where multiple advanced civilizations may observe and interact discreetly across vast interstellar distances. A philosopher promotes the groundbreaking idea that 3I/Atlas may represent a sophisticated sentinel, serving as a stark reminder that our species has been under systematic scrutiny by significantly more advanced intelligences throughout our evolutionary development. This paradigm-shifting revelation fundamentally challenges deeply ingrained anthropocentric worldviews and invites, profound reflection on the true nature of consciousness, intelligence, and existence within a potentially vast, collaborative galactic community. The evidence suggests that what we interpreted as humanity's journey of discovery and exploration has actually been occurring under the watchful eyes of ancient observers who have been cataloging our progress for millennia. This realization transforms our entire perspective on human achievement, technological development, and our future role in what appears to be a much more interconnected and sophisticated cosmic civilization than we ever dared imagine, fundamentally altering our approach to space exploration, scientific research, and our search for extraterrestrial intelligence. James Webb's capture of 3I/Atlas's first real image marks a historic milestone in humanity's encounter with the cosmos and our understanding of our place within it. The implications resonate across science, philosophy, and society, hinting that we may be standing on the threshold of profound discovery and possible first contact with extraterrestrial intelligence. What are your thoughts on these revelations? Share your perspectives in the comments. Subscribe to CI and Y for more cosmic insights, and continue looking upward to the stars where ancient mysteries await our discovery. A decoded transmission from a visitor that has just entered our solar system confirms a chilling reality we've long feared. In 2025, NASA officials confirmed that the interstellar object designated 3Y Atlas is not just a passing comet, it is broadcasting a message. What it says could redefine humanity's place in the cosmos forever. Let's explore this together. The impossible visitor. What if our third confirmed interstellar guest wasn't just wandering through space, but navigating it? When astronomical networks like Pan-STARRS first detected 3I Atlas in early 2025, it shattered every known classification. Unlike previous interstellar visitors, it was traveling at an unusually high interstellar velocity of 45 kilometers per second relative to our Sun, on a trajectory with a hyperbolic eccentricity of over 3.5. But it was its behavior that was truly impossible. It executed deliberate course corrections, moving with a precision that defied any natural explanation. This wasn't a random rock. Its massive coma, a gas and dust cloud stretching 700,000 kilometers across, pulsed with a steady, repeating electromagnetic signal, unlike the chaotic outgassing of a comet like Hale-Bopp. The trajectory it took was impossibly efficient, using the gravitational wells of planets it passed as if it had a complete map of our system, a feat that takes our own probes years of calculation to achieve. The sheer energy required for these maneuvers, conducted without any visible propellant, suggests a technology that operates outside our known physics. As 3I Atlas carved a path through our asteroid belt with surgical accuracy, it became clear this wasn't an exploration, it felt like an arrival. When physics stopped making sense. There are fundamental laws that govern how objects move in space, but 3I Atlas seems to ignore them. Its trajectory showed a smoothness and efficiency that decades of astronomical observations say is impossible for a natural body. Scientists at NASA began using a term that sent shockwaves through the community-piloted behavior. It executed a course correction amounting to a 15 meter per second delta V with no detectable outgassing, a feat that directly violates the Tsiolkovsky rocket equation for an object of its mass. Theoretical physicist Michio Kaku, when presented with the data, noted that the energy required for such a maneuver would be in the terawatt range, equivalent to the entire power output of humanity, sustained for several minutes. To a physicist, this is like watching a multi-ton boulder suddenly levitate and change direction in midair. The violation of this fundamental principle sparked frantic debates within institutions like the Jet Propulsion Laboratory, where teams ran millions of simulations and could find no natural model, not even an exotic outgassing of unseen material, to fit the observed data. This wasn't just an anomaly that stretched our theories, it was a direct contradiction of known physical laws. The object that defied reality. When NASA aimed the James Webb Space Telescope at 3Y Atlas, the data it sent back challenged our understanding of reality itself. The thermal readings were the first red flag. Instead of chaotic heat bursts, 3I Atlas showed a consistent thermal signature of 250 Kelvin, pulsing with a precision of microseconds. JWST's principal investigator for the observation, Dr. Jane Rigby, noted that the thermal stability was unnatural. Webb spectrography then revealed hyper-reflective compounds that appeared artificial, a material with a near-perfect albedo of 0.98, reflecting 98% of all light, something not found in nature. But the most disturbing discovery was a faint electromagnetic pulse repeating every 147.13 seconds. It matched the signature of a real pulsar, PSRB 1919+21, yet the object had no magnetic field capable of generating it. It seemed to be mimicking a signal, a form of cosmic camouflage. Webb's infrared analysis also found structural patterns resembling recursive geometric fractals, leading some to float the terrifying consciousness engine theory, comparing it to theoretical concepts like a Matryoshka brain, but on a smaller, mobile scale. The combination of these impossible features in one object moves it from unusual to unequivocally artificial. two visitors, one terrifying pattern. This wasn't the first time we'd been sent a strange message. The mystery of 3I Atlas deepened when researchers cross-referenced its electromagnetic signature with archived data from Oumuamua from 2017. They found the exact same 147-second frequency had been detected briefly in its tail. The difference was the signal strength. Oumuamua's signal was a whisper in the microjanskis, barely above the noise floor, while 3I Atlas's broadcasting in the millijanskis, 1,000 times stronger. This reframed everything. Harvard astronomer Avi Loeb's controversial theory that Oumuamua was an alien solar sail suddenly gained terrifying new ground. The statistical improbability of two interstellar objects separated by 8 years from different star systems sharing such an unnatural signal is astronomical, suggesting they are part of a coordinated system. Oumuamua's brief, weak signal now looks less like a random anomaly and more like a handshake or ping to test for a response. Now 3I Atlas is answering with a full-blown data stream, implying the test was successful and our civilization has reached a specific technological threshold. When space objects make calculated decisions. The moment we knew for sure we were being actively monitored was the moment it changed course. Just as scientists believed they had mapped its future trajectory, the Very Large Telescope in Chile recorded a subtle but unmistakable 0.05-degree inclination shift, an adjustment of 180 arc-seconds. This wasn't the random drift of a comet. The object veered off its projected arc, aligning with a new vector that brought it closer to Earth's orbital plane. To mission analysts like planetary scientist Dr. Sarah Seeger, the implication was clear: this was a conscious decision. The maneuver occurred just 72 hours after the James Webb Space Telescope began its focused spectroscopic analysis, a time frame confirmed by NASA's Deep Space Network that rules out coincidence. This inclination shift is an incredibly energy-intensive move, and the action wasn't just responsive, it was almost defiant, a clear message that said, "We see you watching us." The mood at the DSN's Goldstone complex as they tracked this impossible change in real time shifted from academic curiosity to profound alarm. Ancient mathematics from the stars. The signal wasn't just a pulse, it was a message written in the oldest language in the universe. Independent cryptographers analyzing the emissions discovered something extraordinary hidden within the narrow band, 0.1 Hz-wide signal. They found precise mathematical ratios, the golden ratio, Fibonacci sequences, and prime number spirals. This is exactly what scientists like the late Carl Sagan predicted an intelligent signal would contain. The signal wasn't just a simple prime sequence, it was encoding the Riemann zeta function, a deeply complex mathematical concept related to the distribution of prime numbers. Furthermore, the signal's modulation, using a complex form of phase shift keying, corresponded to the value of pi to over 1,000 decimal places, an unmistakable beacon of intelligence. Frank Drake, creator of the famous Drake equation, would have seen this as a direct attempt to communicate not just presence, but profound intelligence. This wasn't a simple hello, it was a comprehensive intelligence test, broadcasted across the solar system for anyone smart enough to listen. Organic chemistry from beyond the stars. It wasn't just a machine, it was carrying the very building blocks of life. James Webb's detailed spectroscopic analysis revealed its outer shell was coated in complex carbon molecules, and its NIRSpec instrument found evidence of adenine, one of the 4 nucleobases in DNA, via clear absorption lines between 260 and 280 nanometers. What was alarming was the purity and organization of these molecules. Unlike the chaotic racemic mixture of amino acids found in the Murchison meteorite, the compounds on 3I Atlas showed a 99.7% levorotatory excess, a homochiral signature that is a smoking gun for biological or artificial synthesis. Astrobiologist Dr. Heather Graham at NASA's Goddard Space Flight Center found the conclusion both thrilling and terrifying. The terrifying implication is that if this is a seed ship, its purpose might not be benevolent, it could be preparing the environment for a subsequent colonization effort. The presence of DNA components suggests a biology that might be eerily compatible or dangerously competitive with our own. When Earth responded to the cosmic visitor. We thought we were only observing a distant object, but it was already interacting with our planet. A classified high-altitude surveillance balloon over Antarctica detected an extraordinary event, a powerful 500-megawatt tight-beam microwave burst at 23.4 GHz, lasting 1.2 seconds, originating from the Amundsen-Scott South Pole Station's vicinity. The signal's timing aligned perfectly with another angular shift in 3Y Atlas's trajectory. Moments after the burst, seismic stations recorded ultra-low-frequency rumbles, registering a 1.2 on the Richter scale, but resonating at a perfect 0.0068 Hz, the exact inverse of the 147-second pulse. Dr. Francis Halzen, principal investigator of the IceCube Neutrino Observatory, later reported a statistically significant 3 sigma spike in TeV-range neutrinos from the same location. The synchronization implies the Earth itself is part of a much larger, ancient network that is now being activated, with a dormant relay station buried deep beneath the ice. The asteroid belt death run. Right now, 3I Atlas is navigating a cosmic minefield, and it's doing so with terrifying ease. Its current path takes it directly through the main asteroid belt, traversing the dense Kirkwood gaps at over 60 kilometers per second. Unlike most comets, which have highly inclined orbits, 3Y Atlas is cutting directly through the belt's core. Planetary defense expert Dr. Amy Mainzer, former principal investigator of the NEOWISE survey, noted that its 700,000-kilometer coma is interacting with millions of untracked objects. More astonishingly, minor course corrections have been observed, suggesting it's actively avoiding even meter-sized debris with impossible precision. This avoidance system must be processing the trajectories of over 1.5 million known objects in real time, a feat of computation that dwarfs anything on Earth. Its journey isn't a dangerous run so much as a demonstration of effortless superiority over a hazardous environment, adjusting its path by mere hundreds of kilometers to avoid potential impacts. Rewiring our solar system's neural network. This object isn't just passing by, it may be fundamentally changing the space around us. Data from NASA's Parker Solar Probe, led by scientists like Dr. Noor-e Rawafi, confirms the object is generating Alfvén waves in the solar wind, disturbances measuring several nanoteslas that can transfer energy over vast distances. Scientists at NOAA's Space Weather Prediction Center are concerned these disturbances could amplify the effects of the next coronal mass ejection, potentially increasing the resulting geomagnetic storm's KP index by 2 to 3 points, pushing it from a moderate to a severe event. The charged dust particles it's shedding are acting as charge carriers, creating a persistent conductive path between the object and the sun's magnetic field lines. It is essentially inserting itself as an active electrical component into our solar system's delicate circuitry. The long-term consequences for planetary magnetospheres, including the one that protects all life on Earth, are completely unknown and deeply concerning. The universe has sent us messengers, and we are only just beginning to learn their language. The mysteries of Oumuamua and other interstellar visitors remind us that we are part of a vast, interconnected cosmos filled with wonders we are yet to discover. The journey into the unknown continues. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the frontiers of science. Thank you for watching Sci&Y. When CERN's Large Hadron Collider smashed protons together at unprecedented energies, scientists weren't just hunting for new particles. They were searching for something far more extraordinary: microscopic black holes. These quantum-scale phenomena, predicted by cutting-edge theories involving extra dimensions, could revolutionize our understanding of gravity and space-time itself. Today on Sci&Y, we're unveiling what really happened when the world's most powerful particle accelerator went hunting for the universe's most mysterious objects. The quest for quantum black holes. CERN's scientists embarked on one of the most ambitious experiments in physics history, deliberately trying to create black holes in a laboratory setting. The search for microscopic black holes at CERN represents a fascinating intersection of theoretical physics and experimental reality. Unlike the massive black holes found in space, these quantum black holes would be incredibly tiny, existing at subatomic scales and lasting for mere fractions of a second. The CMS experiment at CERN's Large Hadron Collider has been actively searching for these phenomena since the facility's early operations. According to CERN's official documentation, some theoretical models suggest that microscopic black holes could form when particles collide with sufficient energy, particularly if our universe contains extra spatial dimensions beyond the familiar 3. These theories, including the Arkani-Hamed-Dimopoulos-Dvali model and the Randall-Sundrum scenario, propose that gravity might be much stronger at quantum scales than previously thought. The LHC's proton-proton collisions at energies up to 13 TeV create conditions where, according to these models, space-time itself could briefly collapse into microscopic black holes. If formed, these quantum objects would immediately evaporate through Hawking radiation, producing distinctive particle signatures that CERN's sophisticated detectors could potentially observe. The theoretical foundation. The possibility of creating black holes in particle accelerators stems from revolutionary theories that suggest our universe has hidden dimensions we can't perceive. The theoretical framework for microscopic black hole production relies on models involving extraspatial dimensions. In standard four-dimensional physics, creating a black hole would require concentrating energy equivalent to about 10 to the 19th GeV, far beyond any human-made technology. However, theories like the ADD model propose that gravity might propagate through additional dimensions, while other forces remain confined to our familiar three-dimensional space. This would effectively lower the energy threshold for black hole formation to potentially just a few TeV, precisely within the LHC's operational range. Dr. Lisa Randall and Raman Sundrum developed influential models suggesting that if extra dimensions exist, the fundamental scale of gravity could be much lower than previously thought. These theories emerged to solve the hierarchy problem, explaining why gravity appears so much weaker than other fundamental forces. If correct, when protons collide at nearly light speed in the LHC, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. The mathematics behind these theories is elegant but complex, requiring sophisticated computational models to predict observable signatures. CERN's experimental search. Armed with the world's most sensitive particle detectors, CERN scientists began their systematic hunt for evidence of microscopic black hole creation. The CMS experiment at CERN has conducted extensive searches for microscopic black hole signatures in high-energy proton-proton collisions. Using data collected during the LHC's operations at 7 TeV center of mass energy, researchers analyzed collision events looking for the distinctive particle sprays that would result from black hole evaporation. According to CERN's published results, if microscopic black holes were produced, they would evaporate almost instantaneously through Hawking radiation, creating characteristic patterns of subatomic particles detectable by the CMS detector surrounding the collision point. The search methodology involved examining invariant mass spectra of particle jets, looking for anomalies that couldn't be explained by standard particle physics. Scientists used sophisticated Monte Carlo simulations to model expected black hole signatures, comparing these predictions against actual collision data. The ATLAS experiment has also conducted similar searches, analyzing electron plus jet and muon plus jet invariant mass spectra with 140 inverse femtobarns of collected data. These experiments represent some of the most sensitive searches ever conducted for quantum gravitational effects, pushing the boundaries of what's experimentally accessible in fundamental physics. The surprising results. After analyzing millions of particle collisions, CERN's results challenged expectations and honestly, revealed something unexpected about the nature of reality. The experimental searches conducted by both the CMS and ATLAS experiments have yielded some pretty fascinating results. No direct evidence for microscopic black hole production has been found in the energy ranges examined so far. The CMS experiment's analysis of 7 tera-electron-volt collisions ruled out the existence of microscopic black holes, up to masses of 3.5 to 4.5 tera-electron-volts, for various theoretical models. More recently, the ATLAS experiment search using 13 tera-electron-volt collision data set even more stringent limits, excluding quantum black hole production up to 9.2 tera-electron-volts in the Arkani-Hamed-Dimopoulos-Dvali model, and 6.8 tera-electron-volts in the Randall-Sundrum model. These non-observations are actually scientifically significant because they constrain the parameters of extra-dimensional theories. The absence of black hole signatures at these energy scales suggests that either extra dimensions don't exist as these models predict, or the fundamental scale of gravity is higher than theorized. However, these results don't definitively rule out microscopic black holes. They simply push the energy threshold higher, potentially requiring future collider experiments with even greater energies to test these theories conclusively. Safety considerations and public concerns. The prospect of creating black holes on Earth sparked widespread public concern, forcing scientists to address some pretty fundamental questions about experimental safety. Public fears about CERN creating dangerous black holes have persisted since the LHC's inception, and honestly, they've been amplified by popular culture and social media speculation. CERN has consistently addressed these concerns through comprehensive safety assessments and public education. According to CERN's official safety documentation, any microscopic black holes produced would be perfectly safe because they would evaporate almost instantaneously through Hawking radiation. The fundamental safety argument relies on cosmic ray interactions. High-energy particles from space constantly bombard Earth's atmosphere with energies far exceeding the LHC's capabilities, up to 10 to the 20th electron volts. If dangerous black holes could be produced at LHC energies, cosmic rays would have already created them throughout Earth's 4.5 billion-year history. Dr. John Ellis and other CERN physicists have emphasized that even hypothetically stable microscopic black holes would be harmless because they would interact so weakly with ordinary matter that they would pass through Earth without effect. The LHC Safety Assessment Group concluded that the experiments pose no conceivable danger, with multiple independent reviews confirming these findings. Hawking radiation and quantum effects. Stephen Hawking's groundbreaking theory predicts that microscopic black holes wouldn't grow and consume matter. Instead, they would explode in bursts of quantum radiation. Hawking radiation theory, developed by Stephen Hawking in the 1970s, fundamentally changed our understanding of black hole behavior. According to this theory, black holes aren't completely black but emit radiation through quantum effects at their event horizons. For microscopic black holes, this process would be extraordinarily rapid. Objects with masses comparable to elementary particles would evaporate in approximately 10 to the minus 27 seconds. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. This creates a natural safety mechanism. Any microscopic black holes produced at CERN would immediately decay into standard model particles before they could interact with surrounding matter. The evaporation process would produce a distinctive spray of particles including photons, electrons, muons and quarks, creating detectable signatures in CERN's instruments. Theoretical calculations suggest that the temperature of Hawking radiation from a microscopic black hole would be incredibly high, potentially reaching 10 to the 17th Kelvin. This extreme temperature would cause the black hole to radiate away its entire mass almost instantaneously, making it impossible for such objects to grow or pose any danger to their surroundings. Implications for extra dimensions. The search for microscopic black holes at CERN represents honestly humanity's first experimental probe into the possibility that our universe contains hidden spatial dimensions. The theoretical models predicting microscopic black hole production are, intimately connected to theories of extra dimensions. These models suggest that our familiar three-dimensional space might actually be embedded in a higher dimensional reality, with gravity able to propagate through these additional dimensions, while other forces remain confined to our observable space. The ADD model, which was developed by Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, proposes that gravity appears weak because it spreads out through large extra dimensions. Meanwhile, the Randall-Sundrum model suggests that we live on a three-dimensional brain within a five-dimensional space, with gravity concentrated near our brain by the geometry of space-time itself. CERN's experimental limits on black hole production provide, crucial constraints on these theories. The absence of black hole signatures at current energy scales suggests that if extra dimensions exist, they must be smaller or configured differently than some models predict. These results represent the first experimental tests of quantum gravity theories, providing invaluable data for theoretical physicists working to understand the fundamental structure of spacetime and the unification of quantum mechanics with general relativity. Advanced detection methods. CERN's scientists, have developed some truly revolutionary detection techniques to identify the fleeting signatures of microscopic black holes among millions of particle collisions. The search for these tiny black holes required developing really sophisticated analysis techniques to distinguish potential black hole signatures from ordinary particle physics processes. The CMS and ATLAS detectors use these multi-layered systems, silicon trackers, electromagnetic calorimeters, and muon chambers, to reconstruct particle trajectories and energies with, honestly, extraordinary precision. Scientists have also developed specialized algorithms to identify the high multiplicity particle jets that would result from black hole evaporation, looking for events with unusually large numbers of particles produced in spherically symmetric patterns. On top of that, machine learning techniques have been employed to analyze vast datasets, training neural networks to recognize potential black hole signatures among the billions of collision events recorded. The analysis focuses on invariant mass distributions, searching for resonances or anomalies that just can't be explained by standard model processes. Researchers use Monte Carlo simulations, which incorporate various black hole models, to predict expected signatures, then compare these predictions against real data using statistical methods. The detection challenge is immense. Potential black hole events would be extremely rare, requiring analysis of petabytes of collision data to identify possible candidates among overwhelming backgrounds of ordinary particle interactions. Future prospects and higher energies. As CERN prepares for even more powerful experiments, the search for microscopic black holes is, well, entering a new phase with unprecedented energy scales. The high-luminosity LHC upgrade, which is scheduled for completion in the late 2020s, will actually increase collision rates by a factor of 10, providing vastly more data for rare event searches. This enhanced capability could push the search for microscopic black holes to higher mass scales, potentially reaching the thresholds predicted by some extra-dimensional models. Looking ahead, future collider projects, including the proposed future circular collider, with energies up to 100 TeV, would provide even more sensitive probes of quantum gravity effects. The increased energy and luminosity would allow scientists to explore black hole production at mass scales up to 50 TeV or higher, definitively testing many theoretical predictions. Advanced detector technologies under development like improved calorimetry and faster data acquisition systems will enhance the sensitivity to black hole signatures. Theoretical work is also continuing to refine predictions, with new models suggesting alternative signatures that might be more easily detectable. Really, the combination of higher energies, improved detectors, and more sophisticated analysis techniques may finally provide the experimental breakthrough needed to either discover microscopic black holes or definitively rule out their production at collider energies. The broader impact on physics. Whether CERN finds microscopic black holes or not, the search itself is, honestly, revolutionizing our understanding of fundamental physics and the nature of reality. The quest for microscopic black holes at CERN represents more than just hunting for exotic objects. It's really testing the very foundations of our understanding of space-time, gravity, and quantum mechanics. The experimental limits already established have constrained theories of extra dimensions and quantum gravity, forcing theorists to refine their models and develop new approaches to unifying fundamental forces. The sophisticated detection methods developed for black hole searches have advanced experimental techniques across particle physics, improving our ability to discover other new phenomena. The safety analyses conducted for these experiments have also deepened our understanding of cosmic ray interactions and astrophysical processes. Even negative results provide valuable scientific information, ruling out certain theoretical possibilities and guiding future research directions. The interdisciplinary nature of this research has fostered collaboration between particle physicists, cosmologists, and theoretical physicists, leading to new insights about the universe's structure. As CERN continues pushing the boundaries of experimental physics, the search for microscopic black holes remains a powerful probe of reality's deepest mysteries, potentially revealing whether our universe truly contains hidden dimensions and whether quantum mechanics and gravity can be unified into a single theoretical framework. CERN's search for microscopic black holes represents humanity's boldest attempt to probe the fundamental nature of reality itself. While no black holes have been detected yet, the journey has revolutionized our understanding of physics and pushed the boundaries of what's experimentally possible. If you're fascinated by these cutting-edge discoveries and want to explore more mind-bending physics mysteries, hit that like button, share your thoughts in the comments, and subscribe to Sci and Y for more journeys into the universe's deepest secrets. Thanks for watching. Keep questioning reality.